Good morning, everybody. We finally have a projector, so I think I can start. My name's Halvar. I'm a reverse engineer for a German company called Cybersecurity. We specialize in obscure reverse engineering tools for niche markets. And yeah, I'm going to give a talk on what I think are the issues that we as reverse engineers should try to solve. So in general, this talk is very different from from all the talks I've given so far, because I will not have really much to show. Like, I won't have any tools that work or any bugs that work or whatever. Basically, yeah, I won't show any cool bugs. I'm getting old, I'm losing hair. Bugs get fewer, hair gets fewer. So I can't really disclose that sort of stuff anymore. I don't really have solutions to any problem in this talk. So this talk is essentially a wish list of things that I think are solvable and that I would like to see solved. And for most of the problems that I will be discussing here, I'll give a vague and most likely incorrect idea on how that could be done. And yeah, so it's basically I'll be dumping a bunch of ideas that are all half-cooked and not well thought through to the audience, and hope that a few of you will pick them up and think them through and tell me I was wrong and show me a good solution. So yeah, before we start talking about reverse engineering, we should probably start understanding the concept of engineering. And what is engineering really? Because reverse engineering is the inverse process of that. So yeah, in engineering you have a problem which you would like to solve, and then you design a system and its components and how they interact. And then after you've designed that, you either construct the components or you steal them or you do whatever with them, and you string it all together. And in the end, you integrate it all, and hopefully it works and doesn't collapse. Yeah, so the thing is that we start with a very abstract design or an abstract idea, and then we have a concretization that ends up with a source code. So the source code is really the last step in the entire engineering process. All right. Now, all of us have been involved at some point in some engineering somewhere, and we all know that engineering in practice is not as clean as I just described it is. In essence, you, in many cases, just tie things together and weld them together somehow so that they fit. That doesn't really change that there is an implicit design in source code, or in the code that you have in the end. So it might not actually reflect the design you have on paper, or the design you have in your head, or the design that you should have, but in the end, the code that you have has an implicit design. And also the code that you have in the end is implicitly modularized, meaning there's components of the code responsible for one thing, there's components in the code responsible for another thing, and those are actually separate in the source code somehow. And you have trust relationships which are either explicitly modeled in the design or implicitly there in the code. And oftentimes your code will not reflect the trust relationships you had in the design phase. And yeah, so there's a whole bunch of abstraction that is inside your source code. And this abstraction is really what is most interesting. So reverse engineering. Reverse engineering is the process, like the inverse process of engineering. And perhaps in order to understand this better, we should say what reverse engineering is not. Because reverse engineering is not disassembly. In the sense of that, well, the source code is not everything that is produced in the engineering process. We have all the abstract design, we have all the higher-level concept, we have the relationships, and so forth. The source code is the end product. And the disassembly is not even the source code. So the disassembly does not do anything to actually reverse the engineering process. We just get, well, some assembler code which we can then try to understand. So the end goal of reverse engineering is not to get a clean disassembly or to have a good disassembly or whatever. Of course, you need a good disassembly to really start the reverse engineering process. It's like the first step. But this is not the end goal. And basically, a good disassembly should recover you all things cleanly that you can easily recover from the executable, meaning all the function boundaries, which basic blocks belong to which function, and yeah, that's already it, more or less. Like, that's what the disassembly process should really be giving you. And you should measure your disassembler by its capability of doing that core competency, getting you a clean, good disassembly which groups all the instructions belonging to a function into that function. All right, so what else is reverse engineering not? Reverse engineering is not decompilation. There's a bunch of reverse engineers that I know that think that the end goal of any reverse engineering process is producing code that is recompilable into the same binary. And I strongly disagree on this, because if I give you the source code to Oracle now, you don't understand crap about it. If I give you the source code to Vista now, you don't understand crap about it. Microsoft doesn't understand the source code to Vista, I'm quite sure. I don't think anybody does. So the thing is that decompilation to source will help somebody who doesn't know assembly to reconstruct the higher level abstractions. But it doesn't change the fact that it is really not the end goal of reverse engineering. Because what is the end goal of the reverse engineering is the recovery of the higher level abstractions. All right. So the thing really is that source code itself, when just recovered from a binary, does not help really. Okay, it helps people that are not fluent in reading assembly language. It helps people that, well, to an extent, it might help me read code or whatever, or other people that are just not very good at assembly. But in the end, it's really not the goal to get source code. So the really broad definition of reverse engineering has to be that we want to recover high-level abstractions, meaning, well, we want to basically get all the things from the executable that normally a good and clean design process or engineering process would create, meaning modularization, interfaces, how the components fit together, which components are responsible for what, and so forth. Essentially, reverse engineering should be able to generate, given only an executable, a full documentation of the program and, well, diagrams of how things relate and so forth to make it easy to understand the system. All right. Of course, in this select audience, bug finding is usually the goal. But if we really think about it, realistically, in a few years, I don't know whether it's going to be 5 or 20 or 50, there won't be overflows anymore. Static analyzers are getting very, very strong. The A340 avionics code was proven to be free of out-of-bounds memory access, and that's a significant chunk of code with multiple threads and everything. So we can just say that at some point there won't be the silly overflows or the silly we write out-of-memory thingies anymore. At that point, it comes down to logic bugs. And logic bugs are fiendishly hard to detect automatically and can be detected if somebody understands how the components fit together. So for us as people who are looking for bugs in the long term, we just have to understand massive amounts of the program, or massive parts of the program. If you ever have the chance to speak to Mark Dowd, he's got a very, very interesting perspective on this, because when he looks for bugs, he really understands most of the program first before he does most of the auditing. By the way, Mark Dowd and John McDonald are writing a book on source code review, and it's excellent. If you happen to have your book budget empty, or still book budget available, go and buy it. I'm not getting paid for this, it's just a good book. All right, so the question is, how would we even start to recover high-level structures, like the high-level concepts in an executable? Because when we have the disassembly, all we have is like this big chunk of functions and how they relate in calls to relationships, and we got nothing else really. So perhaps we should start by asking ourselves, what is a piece of software really? And I'm horrible at designing diagrams, so this looks all marketing crap and totally meaningless. But in essence, a program, first of all, consists of modules. Like you have the module responsible for doing the network interaction. You have the module responsible for doing something else. You have the logging module. You have the allocation module, and so forth. So an application consists of a bunch of modules. All right. And each module has a structure in itself, because a module is usually designed that you have an external interface, functions in that module that you can call, and then you have the internal functions, which are being then called from the external interface, and you have external data structures, meaning data structures which the module uses to interact with the outer world, and you have internal data structures. So one of the goals that we would need to have in our reverse engineering tools would be to, well, take an application, separate it into modules, and then for each module, identify what the external interfaces are, identify what the internal functions are, identify what the data structures are, and which ones of these are used to interact with the outer world. All right. This is basically, if you look at software from a non-object-oriented paradigm, which means, well, if you ever try to look at embedded VPN appliances or routers or whatever, you really get these huge, insane systems where you have no concept of modularization from the disassembly. And this is really where this, this question is coming from, because under Windows you at least get like multiple DLLs, which gives you an approximation of modularization. So in general, it's interesting to read books on proper software design. Well, the Dowd McDonald book is not on proper software design, but on bug finding and bad design, but still. And they define a few things that are important about modularization. Specifically, the modules of a program should exhibit loose coupling, meaning they should have very few well-defined interfaces that sanitize input coming in, and they should have strong cohesion, meaning they should do a set of very tightly related tasks. All right, so the question is, can we recover from the executable modules in a manner that they exhibit, well, loose coupling and strong cohesion? We're a little bit luckier in the object orientation, or in the object-oriented paradigm, because if we can reconstruct all classes from an executable, all the inheritance relationships and so forth, we get a large part of the abstract design from that application automatically, just because we have objects which are directly connected then, and so forth and so forth. So actually I think that recovery of the abstract design is easier when you have object-oriented executables, just because you get more information about the design in the executable in the end. If you just compile ANSI, you just get a bunch of functions, whereas in the object-oriented model, you get classes, inheritance relationships, and methods which belong to one class but not to another, and so forth. You get the functions already grouped by functionality by operating on the same class. All right. So the thing is that reverse engineering has historically been mostly done in secrecy and only by a very small number of people. That has changed significantly over the last years. I mean, the sheer fact that we have this many people in this room shows that reverse engineering has grown and matured quite significantly over the past few years. And the thing is that on the engineering side, we have tons of advanced tools. Like we have UML diagramming and generation of code from UML diagrams, and then regeneration of diagrams from existing code, and so forth. On the reverse engineering side, we're a bit stuck in the 80s. Like, we have IDA, and IDA is good, is an excellent disassembler, but it is really not doing any of the higher level things. And well, we don't have all that many other tools. Now, the tool side is changing very slowly now. We are getting a few other tools going. There's a HB Gary's Inspector, there's PyMay, there's BinDiff, there's BinNavi. But to be quite frank, all these tools have a user base of probably, well, I know that BinDiff has a user base of a bit more than 200 people, I guess. Everything else probably has a user base of below 50. And that means that they're extremely tiny in their reach. So reverse engineering has grown, and apparently there's budget for it, otherwise most of us wouldn't be here. So perhaps at some point we can actually afford some real R&D into reverse engineering, meaning solving a bunch of problems that we really should be solving. So what will follow now is my wish list of problems that should be solved, or that I would spend my research money on if I had any. So I hope there's people in the audience that have research money to spend it on. And also I'll volunteer. If you want, you can spend research money on me, and then I'll do the research. But all right. Thing is, with almost all the problems you'll run into here, almost all of them will be, in the worst case, undecidable, in the better case, NP hard, and all this, of course, speaking about the general case. So in general, everything that I propose here will be either undecidable or NP hard. But the thing is that you never meet the general case in real life. You always meet special cases, and for most NP hardness proofs, or most NP hard problems are not NP hard in a random sample. And we don't even get random samples, we get highly structured samples. So let's not be scared about let's not be scared away by the NP hardness of some of these problems in perhaps 2% of the cases. We can solve them in 98% of the cases, we're all fine. All right, so challenge number 0, really, really easy. Given an executable, reconstruct the set of possible return values for each function. That's actually not really a challenge, that's why it's got the number 0. You can do that in a bunch of Python script in about 2 days. But it's surprisingly effective in helping your program understanding if you see a function and your disassembler is telling you, okay, now this function here can return -1, +1, and 0. And that just smells like a comparator. Or this function here can return 0 minus 1 or malloc, and that just like, or the return value of malloc, that just smells like something that's allocating something and giving me an error, if not. Or you automatically extract all the error keys from Microsoft code, like when they return C00053, C0054, 800022, and so forth. So that is really, really easy in almost, like in more than 50% of all cases. Gets a little bit more tricky in others. Not really a challenge, not really that interesting. Let's start with something interesting. Full executable data structure reconstruction. Given an executable, reconstruct all data structures used in the executable. Step 1. Secondly, reconstruct nesting of data structures where you can recover it from the executable code. Thirdly, reconstruct points-to relations between data structure members and data structures, meaning if structure member 5 points to another structure, record that. Then construct a graph from these relations, meaning you have a graph where every node is a data structure. Whenever one data structure refers to another, like as in like a data structure member refers to another data structure, add an edge to this graph. Now, this graph should not only help you greatly in understanding how data structures are correlated. I mean, we all know this from code auditing when you look at like, okay, now they're taking this structure and this pointer and that pointer, and then in that structure they're dereferencing and dereferencing, and you surf through header files for like 5 minutes just in order to find out what the final type of the thing is you're looking at. And that would just be solved if you had a diagram like this. Secondly, in that diagram you could very easily recover recursive data structures like trees and graphs and so forth. So, yeah. And I don't think it's all that difficult. I'm very, very sure that this is doable. I'm very sure that this is doable with, let's say, 2 man-months worth of work. I even have a suggestion for a pseudo algorithm. I don't know whether that'll work. That's really totally pulled out of my ear. And I don't think, well, I'll just try to explain how I would go about this now. Thing with research is you always run into problems, like you always have an idea of how something works, and then you try it, and you get a bloody nose, and you have to rethink it again. So the idea in this case is you take every function in the executable and you iterate over them. Now, for every memory access in that function, you associate those memory accesses that operate on the same data block, like on the same memory region. And then you create a data structure for each of these regions with these offsets in the function. Then, after you've done that, you iterate over all functions again and build argument prototypes for these functions, saying, now this function takes as first argument the data structure number 1. Takes a second argument, the data structure which we've assigned number 2, within this function. Once you've done that, you do a next round where you merge basically all the information. If you know that this function here has a data structure with number 20, which passes on to this function over here as data structure number 25, you merge these 2 data structures. And you iterate over that, and because you're essentially iterating over the call tree, you should terminate in n half steps, where n is the maximum depth of the call tree. In theory. I haven't tried this, so careful. Well, creating the graph from these data structures should then be relatively easy, because you just iterate over the data structures and iterate over the locations where they're being like written to, and check whether they're writing a pointer to another data structure. Should definitely be doable as well. All right, so that was number 1. Challenge number 2. Well, we all know and we all hate object-oriented code. And we mainly hate it because our tools are not adequate. I mean, seriously, doing disassembly of object-oriented code with our current infrastructure is a bit like having to dig holes with chopsticks. You just know it's not the right tool for this. You have all this indirection, you have indirect method calls which you can't easily resolve yet, and so forth. So, challenge would be, given an executable, reconstruct all the classes, like recover all the constructors to classes, from these constructors, reconstruct the class. From the calls to relationship between constructors, you can infer inheritance relationships, which means if I inherit or I derive a class from another class, obviously I'm calling the superclass's constructor. Once you've reconstructed all the data structures and their inheritance relationships, you create UML diagrams from the classes. So by next year, this time, I would like to have something that creates me a UML diagram from a given object-oriented piece of code as executable. Yeah, and then you can merge the UML diagram, which we generate, with the type info diagram generated in challenge 1, and that should go a very long way. I actually think this might be a little bit easier than challenge number 1 because you get a lot more structure in C++ code than in regular C code. And if you're a little bit weenie, you can fall back to being compiler specific. But I think this should also be not, I'm not saying easy, but not too difficult. All right, yeah. The grouping of functions towards these classes, of course, like once you recover the classes, not once you recover the classes, but part of recovery of classes is, of course, recovering all their methods. And you get a whole bunch of methods from the vtables of the class immediately. And then you have to sort out which methods belong where, because you can't just take the vtable and transcend downwards in the call tree and say everything here belongs to that class, just because there might be methods belonging to multiple classes. But in general, this should be, like, one should be able to solve this out. To find methods that are not virtual in nature might be a little bit more tricky, because you might have to actually have a relatively strong data flow algorithm to do this. I don't know. This might be a little bit difficult. A really, really trivial but fun thing to do once you're done, because you have the data structure layout and the type info for the classes, and you have the vtable pointer, you can scan through memory and look for the vtable pointer. Whenever you see it, well, you have a class instance. So you can runtime enumerate and edit C++ objects in memory. I think those of you that like World of Warcraft and those sort of games are just drooling over the idea. So that should work. Okay. I talked about this before, challenge number 3. Automatically decompose an executable into modules. The modules should reflect or exhibit loose coupling and strong cohesion, meaning they should do similar tasks, like within one module, functions should operate on related tasks, and they should have a minimum number of entry nodes which do input sanitization in a form. Then once you can decompose them into modules, try to group them into externally accessible and internal functions. That should be relatively easy. And then the difficult part, separate the data structures into the ones that are used for external communication and internal communication. Yeah, I really don't know how difficult this is. And I really have no clear idea on how to do this. A few ideas that are like the first thing that comes to mind over beers is you could calculate a dominator tree on the call tree, or on the call graph. A dominator tree means that if one node dominates another in that tree, like if one node is a direct predecessor of a node, all paths through the second node have to pass through the first one, which basically means that a dominator tree should be able to identify your gateway nodes in the call tree, in the sense of, if I have an entire module here, and that is only accessible through this function up here, then obviously all these functions down here will be grouped in the dominator tree beneath that function. So basically, I'm not sure whether this will work, but one could try to just calculate a few dominator trees at different points in the call graph, and then take those nodes with a very high out degree and declare them to be gateway nodes to a module. Don't know whether that'll work. Second idea would be try as an optimization problem. You have the entire call graph, and you want to decompose this now into strongly connected components with a minimum number of nodes that you would need to cut away to separate them. The idea behind this is, if you have the big graph, the interface nodes, the external nodes, if you cut them away, you would have disconnected modules, right? So let's try to find the minimum number of nodes that you would need to cut away to separate these things into coherent modules. You probably want, I don't know whether that'll work, just might be an idea. Next idea would be to try to group functions by usage of the same data structures. Meaning you would look at the set of functions, operate, like you would iterate over all data structures in the executable, and look at the set of all functions operating on a certain data structure. And then you would try to create a subset of the executable that has the largest number of common data structures in it, like encloses the largest number of these data structure subsets, and at the same time minimizes the number of nodes in that set. Might work, don't know. Really no idea how this works. Whatever you do there, you probably want to have a parameterized algorithm, meaning something that you can tune, and this is really fuzzy, like this is not hard science. But yeah, I don't know. It's going to be interesting to see whether anybody comes up with anything. All right, challenge number 4. Now we're getting back to the easy stuff. Recovery of template-generated code. Now what's templates really? Templates basically allow you to write code that generically operates on a data structure which exhibits certain properties. And templates are essentially something that the preprocessor will run through. Before I start on going this, I have to tell an amusing anecdote from a German programming contest for, like, the German magazine CT had a programming contest where they had some mathematical problem that they wanted solved, and they said whoever writes the program with the least running time wins some cash prize. And some guy submitted a C++ program that would abuse the template syntax and the template preprocessor to solve the problem on compile time and then just output the result. So compile time was something like 14 hours, and he got disqualified, unfortunately. I don't know why. I thought it was a very, very cute thing. So what are templates really? Templates generate for each, like everybody knows STL list, right? So STL list can have whatever data type inside. And this works similar for basically all templates, that for every instantiation of a template with a certain type, the preprocessor just will generate full copies of the original code with the type replaced wherever you had like the template capital T thingy. So you'll generate exactly the same code, just operating on different classes many times. So the compiler is generating these huge amounts of code, and the reverse engineer has to wade through 300 times the same function, which only differs in offsets when accessing the classes it's operating on. So the challenge here would be detect functions that are the same, except for changing some offsets when they're operating on classes. And that should not be too hard. I think in most cases that should be relatively easy. I don't know, it might work with bindiff style algorithms, it might work with something on a semantic level better, I don't know. All right, now, challenge 5. This is my favorite, and if you want to think about problems that are really, really hard, this is probably one of the hardest you can think of. Given a location T in the executable that we want to reach, and an executable S in the executable that we can already execute, try to automatically craft input so that T is executed. And scenarios where this would be useful is if you have a static analyzer that finds you bugs, you would like to have a program that automatically triggers them. And if you have something like bindiff that the vendor is patching things, you would still not want to spend days trying to reach that code location. You'd like to automate this. And there's other reasons for this. You would like to be able to improve automated testing by improving coverage. It's solved if you can solve this. Now, to make the entire problem a little bit more interesting, we're not looking for one input to reach location S. We're looking for a description of the set of all possible inputs to reach location S. Because, well, what good is it if we have one sample that reaches a target, and whenever we actually try to trigger the bug or whatever, we can't reach it. So we would like to have a description of all possible input sets that lead to a certain location. The first idea how to do this is, or the more or less, the obvious idea to do this would be using genetic algorithms, because you have a very, very clear fitness function. You can measure the distance in basic blocks from your target to your current execution on each input. So given such a good fitness function, one would think that genetic algorithms might be the solution. There's a talk today by Cunningham, Embleton, and Sparks, which is going to use that on it's called Sidewinder, something like that. So that's going to be interesting to see. I personally am not quite sure whether this will work for complex cases, but we shall see. Now, the second idea is a little bit crazier. The second idea implies that you model a path through the executable as an equation system mixing modular arithmetic and Boolean functions like XOR, AND, OR, NOT, and ROR. And you can thus, if you can model the path, and you can model the path in almost all cases that way, you can turn the problem of reaching that certain location into a satisfiability problem. I'm not sure, like, if you've ever had any lecture on theoretical computer science, they drill this thing into you, which is called 3SAT, and how it's NP hard, which is given a large Boolean formula of a certain form. It's NP hard to see whether it's satisfiable. And this is essentially just a satisfiability problem, where you get a large Boolean formula with all the input bits as variables, and then you'll try to solve it. Second possibility would be to regard the entire thing, like you can transfer Boolean formulas into polynomials over f2. f2 is the values of 0 and 1. So you can just transform that into polynomials and perhaps attempt to solve these polynomials. For actually doing this, there's public SAT solvers, which are actually quite good at certain problems. Like while in fact the problem is NP hard for some problems, in practice, a lot of relatively complex SAT problems can be solved even when they have several 100,000 variables. So there's public SAT solvers, or there's OBDD-based algorithms. OBDDs are a special data structure used for representing Boolean functions, meaning functions mapping from a bit string to 0 and 1. And they can be used for representing very large sets of data, meaning if you have you can have 20,000 different values that all satisfy one given OBDD. An OBDD is basically a special form of well, you know, you can, if you have a set of Boolean vectors and you want to represent that set, you can describe that as like an if-then-else relation, basically. If the first bit is set, then do this. If the second bit is set, then do that. And OBDDs are basically a huge decision tree collapsed into a relatively compact graph, which means it can represent very, very large sets of Boolean vectors in a very, very compact manner. All right. We've been doing a little bit of that stuff at home at Sabre, and my guess for difficulty is that if you have no multiplication with two non-constants involved, or basically no multiplication with, multiplication is generally a bitch, and it's not so bad if one of the factors is a small power of 2. And if you don't have multiplication and you really just have add, XOR, roll, if you only have add and Boolean functions, it's relatively, or it's pretty easy. If you have rotations, it can get a little bit harder. And if you have multiplications, it's, I don't know whether it's possible. Now, complicating this entire thing is that having input to exercise a certain path isn't enough, because most paths will depend on application state. So this is the real big complication. We'll have another challenge regarding this later on. Determine which functions to execute to get the application into a certain state. Well, of course, this won't be possible in the general case, but let's say we have something like a network daemon that has a state variable which can have values 0, 1, 2, 4, 5. It should be possible to identify the functions in which these state variables are updated, and then try to, okay, I need state 2 to exercise this path, so I first need to run down this path to set the state accordingly, come back, and then run down the other path. Generally, I think challenge 5 is one of the most difficult problems I can possibly imagine. One of the most fun ones as well, but those two things tend to go together. Challenge number 6. Everybody and his dog is writing VM, translation and VM-based protections these days. And it's getting slightly boring. Somebody, it started out in 96 or 95 with Solar Designer writing these things. And then it was done in a few commercial copy protections in 2000 or up to 2000, 2001. And now it's everywhere. And everybody who thinks it's cool writes like a translator and emulator. And it's getting boring. And we need methods to automatically analyze PE cryptos that take an application, translate it into intermediate language, and then start emulating it. Yeah, and well, I don't really know how that would work. But from my experience, the standard architecture for such a VM-based protection is that you have a VM, and that VM has a context, meaning like the set of registers of that CPU, some sort of data structure. And then it has a decoding loop, where it fetches a new instruction, and then uses that instruction to branch off to the different instruction handlers, and then they update the context somehow, and then it returns. So a trivial and easy thing to do would be just generate a generic debugging framework that each time you see a VM-based protection, just hook into this decoding loop, and that lets you see the changes to the virtual CPU context on every iteration. That's basically just one breakpoint at the right spot in the loop and knowledge of the data layout of the context. All right. Then the difficult part, attempting to automatically recover semantics of the individual instructions. Which means if you have a handler branching off to what is like an addition for the virtual CPU, try to determine automatically that this is an addition. Of course, this can be made arbitrarily hard by the guy writing the VM, But in most cases, I think it will be relatively easy. You'll just see, okay, we're sending these registers in, and now one register contains the value of two registers summed together. I don't know. Thing is, yeah, I really have no clue how hard this entire thing is. I just know that we need infrastructure to build, like to work with these things, because I'm tired of people thinking they're really cool. All right. Challenge number 7. Normal form for code, another difficult one. A lot of the polymorphic engines we see these days are basically just glorified table lookups. So what I do is I have a bunch of instructions, and then I take a block of code, and for each instruction I look up in the table and choose one of a set of possible semantically equivalent representations for that instruction. Meaning I just expand like an add EAX20 to a bit of ugly code like on the right top or on the right bottom. And then you just iterate this. And you can make code arbitrarily ugly by just taking code, throwing it into the morpher, and then throwing it into the morpher again, and throwing it into the morpher again. And your code will just balloon, and the signal-to-noise ratio for the person taking it apart will go crazy. So what we would really like to have is, well, under the assumption, well, in general, of course, this is not possible what I want, but let's say that the translator is not allowed to add memory access, and the translator is not allowed to do self-modifying code. So any substitution which we do here has to just substitute one instruction with a set of others that don't access memory and that don't self-modify. Under that assumption, can we build a reduction that takes a bunch of code and reduces it to a common normal form? Meaning that if I have two code sequences S and S dash, which were both derived from the same source, then I run my reduction relation from them, and I get not necessarily the source, but I get the same normal form in the end. Because if you can do that, you can just strike down 85–90% of all the polymorphic engines that I've seen. Because, well, you just take one sort of polymorphic thingy, and then you reduce it, and you take the other polymorphic thingy, and you reduce it, and then you can compare the results. All right. I'm not sure whether this is possible. It sounds like a really fun project, though, and for those of you who are a little bit more theoretically inclined, that might be something to spend a bit of time on. All right. Challenge number 8. This might actually be relatively easy. Visualizing call graphs is quite important for understanding programs. So we have a graph with like a function, and then all the functions that are called from this particular function. And the disadvantage of this view is while we see that this function here calls these other functions, we lose all concept of ordering. And implicitly in the function calls to subfunctions are ordered. Meaning it makes a great difference whether I call string length malloc memcopy, or whether I call memcopy malloc string length. Like there's just, from the semantics, like trying to understand why are we generating the call graphs in the first place? We want to understand the program. So when we want to understand the program, we want to recover semantics by just looking at what functions it's calling. And within each function, the subfunction calls are ordered, and we lose all that by our current representation in the call graph. And the question is, can we find a visualization mode that keeps us and visualizes for us the concept of the order of the subfunction calls within a function? I don't know. I think it should be relatively easy, but I don't know. 10 minutes, cool. Challenge number 9. Given an executable that is a network daemon that does some sort of protocol parsing, attempt to construct a state diagram telling us which functions can be reached, like, okay, under the assumption that we can identify the state variable, which is going to be an integer of some sort. Can we generate a diagram telling us which functions are reachable in which protocol state, and which functions can be used to move the protocol state to another state? Essentially trying to generate a form, like a sort of diagram from the executable telling us, now we have this CPU in protocol state, and from this protocol state we can move to that protocol state by use of this function, and to that protocol state by use of that function, and we can't go from this state to the other states. Okay, because when it comes down to us no longer having overflows, we'll have to do a lot of protocol analysis, that's for sure. And protocol analysis, well, I end up drawing these sort of diagrams on paper anyhow when I try to do these sort of things. So might as well try to do this automatically. Yeah. I don't really know how hard this is going to be. I think it is going to be terrifically hard in most of the cases. But if it works in about 40% of the network daemons, or just in special cases, like if it can save me a week of work on 2 or 3 daemons I've been working on, or it's more than a week of work. If it can save me a month of work on a few daemons that I've been working on, then it should be worth it. All right. Challenge number 10, semantics-based library signatures. Would be nice to be able to recognize a string copy even if it doesn't have the same byte signature as a string copy. It would be nice to recognize a string copy if the programmer has decided to hand roll it. Which means I would like to have semantics-based library signatures. And something like, I want to automatically be able to recover stuff like, this function here does an insert into a linked list. And I don't know how to do this, but one of the ideas would be to view a function as, like, memory is an abstract graph. And try to view a function as an operation on this graph, modifying this graph somehow. And then see whether we can match functions based on this modification of the memory graph. I have really no clue how good this would work. And I think for many functions you just wouldn't be able to do it. But if we can do it for hand-rolled string copies, then that's already very, very valuable. And if we can do it for stuff like insertions or removals from linked lists and so forth, that's damn useful. All right. Number 11, something that's not really serious yet. Once we have all these things, build a static analyzer, string it together with an input crafter, and then try automated exploitation once you trigger the bug. That won't happen. I don't know. If it happens, it's going to be amusing. But yeah, let's just skip this slide. All right, I'm nearing the end of my talk. There's a few other things that I would like to say. In order to work on these things, we, as the reverse engineering community, need some sort of data format in order to properly store disassemblies. Because the problem we have now is we have a gazillion of closed small tools. We have the big juggernaut IDA, but none of the tools want to talk to each other, and IDA doesn't want to talk to anybody else as well unless you write plugins. So it might be a good idea to have a generic storage that generically stores disassemblies, like a SQL schema in which you can just dump disassemblies and then operate on them. And yeah, so such a SQL schema would string many different or would allow stringing many different tools together to just operate on one big database, and it would also make managing many disassemblies in a larger team easier, because you wouldn't have like 20 IDBs on each hard disk, but one database server which you can then lose in a power out. All right, so we at Sabre have spent a few months actually drawing up such a schema, and we had originally intended to publish it here. But us being a small company and not very good at management and stuff at the moment, we are behind in documenting the schema. So we have it working, we're dumping into it, and it's very, very generic. I can't imagine, well, the one assumption that it makes is that you have a flat address space. But outside of that, I can't imagine many things that can go wrong with this schema at the moment. And we'll publish it in the next 2 or 3 months as soon as we have a good documentation for it. And we're porting all the tools that we're building to operate on the database format instead of only on IDA. And we're inviting all people to just port the tools to use the database format as soon as we publish it. And just hold on a bit while we give you some documentation, because without documentation, reverse engineering SQL schemas is not going to be fun. All right. Any questions? Yes? Yeah, the question. Yeah. Yeah, definitely. The question was whether it makes sense to break the harder problems, like whether it would make sense to break those problems where we don't know about the exact difficulty, at least down into well, being able to classify which bits of the problem are easy and which ones are hard for which cases. Correct? And I think that makes total sense. Yes. Any other questions? Yes.
This one's an easy one. On number 8, your call graph ordering. Yeah. Do you think simple edge labels would be sufficient?
I don't know. Do you immediately, when you look at an edge label, grok it? I don't. So I don't know. All right.
Chris?
Oh, Chris, yes.
Again, with your call graph ordering and stuff, one of the problems you run into there is you might call malloc string copy and stringlen, but if those are in conditional blocks, you still have to order.
Well, you won't have a
Reachable
yeah.
within the initial function. So
You won't have a proper ordering. You'll have a partial order on the set. All right. Any other questions? Then thank you, and I'll be open for more questions over beers later.